Do you ever got this doubt? How your phone unlocks with your face, how Instagram filters recognize facial features, or how self driving cars detect lanes and pedestrians? What if I told you all of these use the same kind of brain inspired technology, a special type of deep learning model called Convolutional Neural Network or CNN? CNNs are the secret behind computer vision, helping machines see and understand images like we do. In today's video, we'll take a clear, beginner friendly yet technical journey into the CNNs. We'll break down what's inside a CNN, how each layer works, and how they learn to recognize everything from digits to diseases. So grab a cup of coffee and let's unlock the black box of CNNs. Let's start simple. A CNN is a type of artificial neural network designed to work with image data. In a regular neural network, we flatten the image into one long vector. But with CNNs, we preserve the 2D structure of the image. Why? Because spatial patterns like edges, structures, textures, and shapes matter in images. A CNN can automatically and adaptively learn spatial hierarchies of features. It starts by detecting simple edges and then gradually builds up to complex shapes and objects. CNNs are widely used in tasks like image classification, cat or dog, object detection, where is the traffic light, facial recognition, is it you? Medical image diagnosis. But what makes CNN so powerful is what happens inside them. A typical CNN is made up of three types of layers: convolutional layers, pooling layers, fully connected or dense layers. Each layer plays a unique role in feature extraction and prediction. So imagine this: you feed in a photo of a dog. The CNN does the following. First, it detects edges using filters. Then, it identifies shapes like ears and eyes. Finally, it concludes, hey, this is probably a dog. Here is the flow of data. First, input image, convolution, activation, pooling, repeat, fatten, dense, and output. Sounds simple, right? Now, let's unpack each component in detail. The convolution layer is where CNNs get their name and power. So, what happens here? You have an image, say 32 by 32 pixels. The convolution layer slides a small filter or kernel, say 3 by 3, across the image. Each filter looks for specific features like vertical edges, horizontal lines, or curves. These are learned automatically during training. A filter multiplies pixel values by its own weights and produces a feature map, a condensed filter version of the image. You can have multiple filters in one layer, each detecting something different. Important concepts here are stride, how far the filter moves, padding, whether we keep the output size the same. The convolutional step preserves spatial relationships, which is crucial for recognizing shapes. After convolution, we apply an activation function. The most commonly used one is ReLU, rectified linear unit. Its formula is simple: f of x equal to max of 0, comma x. Why do we need it? Without activation functions, your CNN would just be a linear model. It wouldn't be able to learn complex nonlinear relationships. ReLU introduces nonlinearity and makes a model more powerful, which allows them to learn abstract features. Now let's reduce the size of the data but without losing important information. Enter the pooling layer. Pooling shrinks the feature maps while retraining the most important information. Max pooling takes the maximum value from each region, say 2 by 2. Average pooling takes the average. This helps reduce computation, prevents overfitting, and makes the CNN more robust to small changes in the image. Think of it like summarizing information in a paragraph, you still keep the essence. Once we have extracted all the features using convolution and pooling, we flatten the 2D data into a 1D vector. This vector is then passed to a fully connected or dense layer, just like a regular neural network. These dense layers learn to combine features and make decisions. Does this combination of edges and textures look like a dog? The final layer usually has a softmax activation to produce probabilities for each class. Now let's talk about learning. How does a CNN know what to do? Training a CNN involves forward pass. Image goes through the layers. Loss calculation. How wrong was the prediction? Backward pass. Back propagation. Errors flow backward. Weight updates using gradient descent. The CNN adjusts It's filtered values and weights over many epochs using label data. Over time, it gets better and better at recognizing patterns. Think of it as trial and error on steroids across thousands or millions of images. Let's see a quick example using the MNIST dataset. It contains 70,000 grayscale images of handwritten digits 0 to 9. We feed a 28 by 28 image into the CNN model. Convolutional layer detects strokes and curves. Pooling layer reduces size. Fully connected layer makes a prediction. The CNN learns to identify the digit based on learned patterns, not memorized pixels. CNNs are used everywhere today. Self driving cars use them to detect lanes and traffic signs. Medical AI uses them to detect tumors in X rays and MRIs. Your phone uses CNNs for face unlock. Social media apps use CNNs for filters and face swaps. In fact, any mission that sees or recognizes something probably uses CNNs. To sum it all up, CNNs are the backbone of modern computer vision. They work by scanning images for patterns layer by layer, from simple edges to complex objects. If you understand CNNs, you understand the core of how machines interpret the visual world. If you enjoyed this breakdown, hit the like button, subscribe, and comment below with what you want to learn next. Stay curious and keep learning.